Ever wonder why your coffee gets cold if you leave it sitting too long? Or why your ice cream melts on a hot day? The answer lies in the laws of thermodynamics. Welcome to the intriguing world of thermodynamics. It's not just a fancy term scientists throw around. It's a fundamental concept that governs the flow of energy, and it's happening all around us. You see, thermodynamics is a branch of physics that deals with the relationships between heat and other forms of energy. In essence, it's the science of energy transfer and how energy affects matter. Imagine for a moment a hot cup of coffee sitting on your table. Over time, it loses its heat and gets cold. Why does that happen? It's because of the first law of thermodynamics, which states that energy cannot be created or destroyed, only transferred or changed from one form to another. In the case of your coffee, the heat energy is transferred from the coffee to the cooler surrounding environment until both reach the same temperature. That's thermodynamics in action, and it's not just about heat. Thermodynamics also explains why your car runs or why your refrigerator cools your food. The laws of thermodynamics govern how energy is converted from one form to another, be it in mechanical work, heat, or even electricity. Think about ice cream on a hot summer day. It melts, right? That's the second law of thermodynamics at play, stating that energy spontaneously spreads out from where it's concentrated to places where it's less concentrated, unless something is there to prevent that. Thermodynamics is everywhere, from the smallest atom to the largest galaxy, from your kitchen to industrial power plants. It's part of the fundamental framework that describes how our universe works. So next time your coffee gets cold, remember, it's not magic, it's thermodynamics. You've heard it before. Energy cannot be created or destroyed. But what does this really mean? Well, it's the core principle behind the first law of thermodynamics, a fundamental rule of our universe that governs how energy behaves. This law states that energy in all its forms can't just appear or disappear into nothingness. It has to come from somewhere, and it has to go somewhere. Let's think about it in terms of your everyday life. Imagine you're charging your phone. You plug it into the wall and voila, your battery level starts to rise. But where is this energy coming from? It's not being created out of nowhere. The electrical energy that's charging your phone originated from a power plant, maybe one that burns coal or uses nuclear fission. In those plants, energy stored within coal or atomic nuclei is transformed into electrical energy, which then travels along power lines until it reaches your phone. Or consider cooking a meal. You're not creating heat from nothing when you turn on the stove. The heat energy that cooks your food originally came from the natural gas or electricity that powers your stove. And before that, the natural gas was formed from ancient organic matter deep under the earth, while the electricity might have been generated from wind, water, or sunlight. In both these examples, energy isn't being created, it's being transformed from one form into another, and that's what the first law of thermodynamics is all about, energy conservation. The total amount of energy in a closed system remains constant. It can change form, yes, but it can't vanish or come from nothing. In our universe, energy is a precious currency. It powers everything from our bodies to the stars in the sky. But just like the money in your bank, it can't be conjured out of thin air. It has to come from somewhere, and it has to go somewhere. So remember, just like your bank account, energy can't be created out of thin air. It has to come from somewhere. Ever notice how a hot cup of cocoa cools down in a cold room? This is an example of the second law of thermodynamics at work. The second law of thermodynamics is a fundamental principle that governs the flow of energy. It states that energy, or more specifically heat, will naturally flow from a region of high temperature to a region of lower temperature. This is why when you leave that hot cup of cocoa in a cold room, it doesn't stay hot forever. The heat from the cocoa is transferred to the colder air in the room until they reach a balance, or equilibrium. Now let's take this concept a bit further. Imagine a cold winter's day, and you're inside your home with a roaring fire going in the fireplace. The room starts to feel warmer, right? Well, that's the second law of thermodynamics in action. The heat from the fire is spreading out to the colder parts of the room, warming up the air. But it doesn't stop there. The heat continues to move, flowing out from the warm room to the colder parts of your house. It seeps under doors, creeps up the stairs, and sneaks through cracks. This is why when you have a heat source in one part of your house, like a stove or a fireplace, the whole house can start to feel warmer. Now, what if you could control where that heat goes? That's where things like heat engines, refrigerators, and air conditioners come into play. These machines manipulate the natural flow of heat, using it to do work or to cool down a space. But that's a topic for another scene. The second law of thermodynamics is a constant dance of energy, a continual flow from hot to cold. It's happening all around us all the time in ways we often don't even notice. So the next time you're warming up by a fireplace, think about the second law of thermodynamics. It's the reason you're feeling cozy. Have you ever wondered if there's a limit to how cold something can get? The answer lies in the third law of thermodynamics. Let's dive in. The third law of thermodynamics essentially states that as you approach absolute zero, the entropy or disorder of a system approaches a minimum value. Now, what does this mean? Well, consider a perfectly ordered system like a crystal at absolute zero, where all the atoms are perfectly aligned. According to the third law, this system would have zero entropy. But here's the catch. The third law also implies that it is impossible to reach absolute zero through any finite number of processes. Absolute zero, or 0 Kelvin, is the theoretical temperature at which particles stop moving altogether. But in reality, particles never truly stop moving. Even in the coldest place in the universe, the Boomerang Nebula, where temperatures drop to just 1 degree above absolute zero, there's still some movement. Why is this? It's due to something called quantum mechanical effects. Even at absolute zero, particles exhibit a phenomenon known as zero-point energy, a fundamental and unavoidable property of quantum systems. This means particles are always jiggling around a little, even at temperatures as low as absolute zero. So, if reaching absolute zero is impossible, what's the coldest we can get? Scientists have managed to cool a piece of rhodium metal to 100 picokelvins, or a tenth of a billionth of a degree above absolute zero. At these temperatures, matter starts behaving in strange ways, exhibiting quantum properties on a macroscopic scale. So while we can cool things down to incredibly low temperatures, we can never quite freeze the motion of particles completely. This is a fascinating consequence of the third law of thermodynamics and the peculiar nature of the quantum world. So, while we can get very, very cold, absolute zero remains just out of reach, thanks to the third law of thermodynamics. Why does a car engine heat up when you drive? Or, why does your computer get hot when you use it for a long time? This is all because of heat capacities and heat engines. Let's dive into this fascinating world, shall we? Heat capacity is a measurable physical quantity that characterizes the amount of heat energy required to change the temperature of an object by a certain degree. It's like a thermal sponge soaking up the energy and then releasing it as heat. The bigger the sponge, or in this case, the greater the heat capacity, the more energy it can absorb before it starts to get hot. Now imagine that thermal energy as a crowd of people. Heat capacity is like a concert venue. A small club might get packed quickly, making it hot and sweaty in no time, just like an object with a low heat capacity. A larger venue, on the other hand, can accommodate more people before it starts to feel cramped and warm, much like an object with a high heat capacity. So, what does this have to do with your car engine or computer getting hot? Well, these are examples of heat engines. A heat engine is a device that converts thermal energy into mechanical work. In a car engine, for instance, the heat produced by burning fuel is converted into the mechanical work of turning the wheels. In your computer, the processor turns electrical energy into computations, but in the process, it also produces heat. That's where heat capacity comes into play. Materials with high heat capacities, like the metal in your car engine or the silicon in your computer chip, can absorb a lot of energy before they start to heat up. But even they have limits. As they absorb energy, they get hotter and hotter until they reach a point where they can't take in any more without overheating. So the next time you feel the heat from your car engine or computer, remember, it's all part of the fascinating world of heat capacities and heat engines. Have you ever wondered why it's so hard to keep things organized? That's entropy at work. Entropy is a fascinating concept that measures the disorder or randomness in a system. It's a fundamental part of the second law of thermodynamics, which states that the entropy of an isolated system always increases. In other words, things naturally move towards chaos rather than order. Let's use the example of a teenager's room. It's a universal truth that a teenager's room tends to get messy over time. Even if they clean it up, give it a few days, and it'll likely be a mess again. This is a perfect example of entropy in action. The room, left to its own devices, will naturally trend towards disorder. Another everyday example is melting ice. When ice melts, it changes from a structured, ordered state to a more disordered one, water. This increase in disorder is an increase in entropy. But why does this happen? To understand that, we need to look at the microscopic level. Each molecule in a system has a certain amount of energy. This energy can be in the form of movement, or it can be stored in the bonds between atoms. When a system is left to itself, the energy tends to spread out and distribute itself as evenly as possible. This leads to an increase in disorder, or entropy. Entropy also has a big impact on the efficiency of machines. A machine can't convert all of its input energy into useful work because some of that energy will always be lost as waste heat. This is another manifestation of the second law of thermodynamics. You can't get something for nothing, so entropy isn't just a theoretical concept, it's a fundamental principle that governs how energy moves and changes in our universe. It's the reason why time only moves in one direction, why machines can't be 100% efficient, and why your room tends to get messy. So, the next time you're struggling to clean your room, blame it on entropy, the universe's tendency towards disorder. Why does your refrigerator stay cold, or your air conditioner keep your house cool in the summer? The answer lies in the laws of thermodynamics. These everyday appliances, your refrigerator, air conditioner, and heat pump, are essentially heat engines working in reverse. Instead of converting heat into work, they use work to move heat from a cooler area to a warmer one. This is the fundamental principle that keeps your food fresh and your home comfortable. Let's take a closer look. Your refrigerator, for instance, works by evaporating a refrigerant, a substance with a very low boiling point. This evaporation takes place in the fridge's coils, absorbing heat from the inside of the refrigerator and making it cold. The refrigerant then travels to the outside coils where it condenses, releasing the absorbed heat into the room. Air conditioners operate on a similar principle. They absorb heat from inside your home and expel it outside, effectively lowering the temperature. Indoors, they use a refrigerant to absorb and transport the heat, just like a refrigerator. Now, what about heat pumps? Well, they're like air conditioners, but with a twist. In the winter, a heat pump can reverse its operation, absorbing heat from the outside air, even when it's cold, and releasing it inside to warm your home. All these appliances operate with remarkable efficiency. Thanks to the laws of thermodynamics, they transfer more heat than the energy they consume, making them a practical choice for temperature control. However, it's important to remember that while these systems are efficient, they're not perfect. They still require energy to operate, and some of that energy is inevitably lost as waste heat. This is a consequence of the second law of thermodynamics, which states that no process can be 100% efficient. So the next time you enjoy a cold drink from the fridge or the cool air from an air conditioner, remember, it's all thanks to the laws of thermodynamics. Ever wondered why no machine is 100% efficient? Carnot's principle explains why. At the heart of this principle is the idea that no heat engine can be more efficient than a Carnot engine operating between the same two temperatures. This might sound a bit technical, so let's break it down. A heat engine, in simple terms, is a device that converts heat energy into mechanical work. Think of your car engine or a power plant. These machines are all examples of heat engines. They work by transferring heat from a high-temperature source to a low-temperature sink. And this difference in temperature is what allows them to do work. Now here's where Carnot's principle comes in. This principle states that the efficiency of a perfect heat engine, a Carnot engine, depends only on the temperatures of the heat source and the heat sink. The higher the temperature difference, the greater the efficiency. But here's the catch. Even with an infinite temperature difference, the efficiency of a Carnot engine can never reach 100%. Why is this so? Well, the answer lies in the concept of entropy, which you can think of as a measure of disorder. The second law of thermodynamics tells us that in any energy transfer or transformation, the total entropy of a system can only increase. In other words, some amount of energy will always be lost as waste heat, increasing the disorder of the system. So, when a heat engine operates, some of the heat energy it uses can't be converted into work. It's lost as waste heat, and this loss is what caps the efficiency of the engine. In the real world, the efficiencies of heat engines are much lower than those of Carnot engines. Factors like friction and other mechanical inefficiencies further reduce the actual efficiency. So while we can strive for efficiency, Carnot's principle reminds us that there's always a limit. Another fascinating aspect of the laws of thermodynamics. So why does your coffee get cold? Why does your computer heat up? Why is it so hard to keep your room clean? It all comes down to the laws of thermodynamics. In this journey, we've explored the fundamental laws of thermodynamics, from the concept that energy cannot be created or destroyed, to the flow of energy from hot to cold, and even the elusive absolute zero. We've delved into the workings of heat capacities and heat engines, and we've grappled with the measure of disorder, otherwise known as entropy. Remember when we discussed that energy cannot be created or destroyed, only transferred or converted? That's the principle that keeps your coffee from staying hot forever. The heat energy from your coffee is transferred to the surrounding air, making your coffee colder and the air slightly warmer. And what about your computer heating up? That's due to the second law of thermodynamics. Energy flows from hot to cold, and in the process of running complex calculations, your computer generates heat. That heat in turn is dissipated into the surrounding environment, raising the temperature of your computer. Keeping your room clean, on the other hand, is a constant battle against entropy. The universe tends towards disorder, and your room is no exception. It takes constant energy input, your effort, to keep things in order. Without it, chaos ensues. We also explored the efficiency of refrigerators, air conditioners, and heat pumps, all of which exploit the laws of thermodynamics to cool or heat our environments. They all use energy to move heat from a colder place to a warmer place, defying the natural flow of heat and making our homes comfortable. And finally, the limit of efficiency, or Carnot's principle, shows us the maximum possible efficiency any heat engine can achieve. This principle underlines the balance of energy in the universe and reminds us that there's no such thing as a free lunch. So, the next time you see energy in action, remember, it's not magic, it's thermodynamics.